But then comes the pesky question of how do we deal with calculating resultant forces on curved objects? It's actually not as hard as it sounds. Well, first of all, I think that this is not something that's super important for very complicated structures, because in the case of very complicated structures, you'll generally have, like a SolidWorks file or a finite element simulation for, complicated things where you can literally do the pressure integration within those kind of programs. But for simple calculations that you can do by hand, this type of problem tends to come up. So a lot of times you have something that is submerged that's curved, but there may be a column of water on top of it before the curved object even starts. So the trick here is to actually divide and conquer. So what we're going to do is imagine that we're going to divide up the regions of liquid into basically 3 different kinds of forces. So we're going to basically create a rectangular prism worth of fluid above which, before the part starts. And up there, it's really easy to calculate how much force is being exerted by the fluid because it's just equal to the weight of the fluid. So that would be mass times gravity of the upper region. So you can either do that by calculating, rho times g times the volume gives you the weight. Or you can equivalently calculate the pressure at the bottom face of that, which is rho times g times the depth of the liquid up to that point times the cross-sectional area of that little dashed red line that I'm drawing. In addition to that, there's an amount of fluid that acts in the lower portion of the fluid. So basically whatever that black line has to support the weight of all the liquid above it as well. So there's a mass times gravity for the lower region as well that acts at its center of gravity, which is usually, so in that case it's harder to calculate because it'll be offset from sort of the center line of the prism, and it'll depend on the shape of the object. But you can calculate it, and that force would act basically along that line in order to counterbalance the weight of the weight of the fluid above it. The other force that acts on the object comes from a horizontal force that you can consider from sort of the vertically projected plate that is the left side of this control volume. So if we imagine that there is a plate sitting on the left side here, we can calculate the horizontal force that would be on it as rho g h, where h is the depth at the centroid of that plate, but it of course acts at the center of pressure of that plate, which is not super hard to calculate. So we learned a method to do that previously that basically requires you to know the moment of inertia of the plate. It might be a little bit more complicated if the projection of the curved surface does not form like a rectangular plate. Like if I'm drawing the curved surface as sort of a cylinder, but if it is a more complicated shape, then when it projects, onto a 2-dimensional surface, that green thing may not actually be a plate. It may be like a semicircle or whatever complicated shape it projects onto. But in any case, you can calculate the horizontal force as rho times g times the depth at which the center of gravity of that projection is. That will act at the center of pressure of that 2-dimensional projection. So to summarize that, basically there will be 3 forces that we're breaking this into. 2 vertical forces, one from this upper region before the curved object starts, and one just beneath it, caused by the weight, the more complicated weight distribution in the curved region. So basically, we do a volumetric integral, to calculate the center of gravity of that object and the total volume of fluid up there, and we can figure out, how big the force is by calculating mg, and where it acts by knowing the center of gravity. And the third force comes from the projected area onto that back green face, so into a 2-dimensional plane. And that's easy to calculate. It's rho gh, where h is the center of gravity of the plate, the projected plate, and the force itself doesn't act there, it acts at the center of pressure on that plate, which we previously learned how to calculate. And so then if you put that all together and sort of isolate the curved object that you want to calculate the resultant force on, what you can do is imagine that, that horizontal force acts at, a location, let's say the center of pressure, and you can just kind of slide that force on over as if it touches the object that you want to calculate the resultant force on. Why does sliding the force over along the line of the center of pressure work? Well, I mean, the objective of figuring out where the force acts is to make sure that it produces the same moment. So it has to have the same moment arm. So as long as I move a vector parallel to its line of motion, I don't change any of the moments that would be created by it. So I can just sort of slide the forces along their line of action until they touch the object. And then when I'm done, instead of having one resultant force, which is like a vector, I'll end up with 3 of them. 2 horizontal ones plus 1 horizontal, what did I say? two vertical ones and 1 horizontal one that you can use to do whatever statics calculations you need to do.